Friends, today we will discuss the 18th lecture in the NPTEL course titled Offshore Structures Under Special Loads, including Fire Resistant Design. Today in this lecture we are going to discuss about the analysis of offshore structure example under earthquake loads. In the last lecture we discussed that earthquake loads can be prescribed using power spectrum. We have discussed the fetch parameters and the control equation for estimating the earthquake load. We said Kane-Tajimi power spectrum is an idealized application to use in offshore structures. Today in this lecture we discuss about the application of this problem on an example study and see what would be the consequences caused by the earthquake forces on offshore structures. To take an example, we will consider a tension leg platform. We all agree that tension leg platform is a compliant offshore structure. Some important characteristic of its behavior can be recollected at this moment. It is actually form dominated design. In sense, as per the design, the buoyancy force exceeds the weight of the platform and that is equated with the tension in tendons with the platform to equalize the buoyancy. So, I have a top side with all details which we say the flare boom, the crane, the living quarters and the drilling derrick, which is now assembled with a column member and a pontoon member. For the mean sea level to remain here, the system remains afloat because the buoyancy, which is actually proportional to the submerged volume of the members, is so high, so that the weight of the platform is lower than the buoyancy, which makes the platform to remain afloat. Of course, to maintain the station keeping of this platform, we actually hold it down in position using tendons. They are always in tension. So, they are called tension leg platforms. The difference between the buoyancy and the weight is compromised or compensated by the tendons forces, which are called initial pretension So, it is very clear in this application that the platform is expected to undergo a large displacement. So, by design it is expected to undergo large displacement, which makes it very compliant. Because of this displacement, which makes it relative with respect to the waves, forces on the members are reduced. So, that is the first issue we have. The second issue, if you look at the degrees of freedom like x, y and z axis, let us mark again the platform with the column members and the pontoon members and the top deck, with all topside details whatever we have there at the CG of the platform. Let us mark the axis. Let us say this is x axis, y and z axis. This becomes my wave direction. So, the platform undergoes surge whose period is about 100 seconds. The platform undergoes sway displacement whose period is again 100 seconds. The platform undergoes heave displacement in z axis whose period is about 2 to 5 seconds. The platform also undergoes roll degree of freedom whose period is about 2 to 5 seconds. The platform also undergoes pitch rotation whose period is again 2 to 5 seconds. The platform undergoes rotation about the vertical axis which is called as yaw motion whose period is about 70 to 90 seconds. So, from this we already realized that the platform is flexible in horizontal plane because having large periods in x, y displacements and having large period in yaw rotation makes the platform flexible in horizontal plane, whereas the platform remains stiff in vertical plane. This is mainly due to heave displacement or heave period being very low and of course, rotations about x and y axis, that is roll and pitch periods also being very low. So, it remains stiff in vertical plane and remains flexible in horizontal plane. Therefore, TLPs are otherwise called as hybrid platforms. Now, under this background, if I have a platform of this order and try to apply an earthquake force, if the earthquake loads cause displacement along x and y, it is not of a great botheration. Because anyway the platform has to remain flexible in horizontal plane. If earthquake forces cause displacement, if they cause displacement in vertical plane, this has got some serious consequences. First, the vertical plane displacement changes buoyancy, in turn changes T0, in turn changes stiffness and in turn results in pull out of tethers. Why? Because the axial value or the displacement because of the axial value due to axial pull, if exceeds T0 permissible, or let us say very specifically axial stiffness, then tethers may fail. When tethers fail, that may result in flotation of the platform, which can in turn affect the functional requirements of the platform. So, friends, we must now see whether these earthquake forces, which usually causes displacement on the seabed, which induces force on the body, will result in any vertical displacement or not. Now, there is a very fundamental intuitive question we have. If I have a platform which is supported and station positioned, let us say by tendons which are in axial tension of a very high value, when this is my mean sea level, when seabed results in earthquake forces and let us say in all the 3 degrees, let us say earthquake forces, that is x double dot g causes displacement in all 3 axes, let us say. Okay. There is a very extensive amount of water body available here, because we are talking about deep water platforms, because offshore structures of compliant nature are essentially recommended for deep waters. Let us say the water depth is about 600 meter to as high as 1100 meters as far as TLPs are concerned. So, there is a very good water cushion, and these are only cables or tethers which are actually not any load carrying members as far as wave loads are concerned. Please understand, tendons do not account for lateral loads. The fundamental function of tendon is to hold down the platform in position through very high axial pretension, which we call as TGL. So, they do not resist the lateral forces. As usual, earthquake loads, if they are acting lateral, they are not supposed to resist them. So, the resistance of the lateral force essentially comes only from these members which are immersed, or let us say if this is a member what you are considering, the member is partially immersed. Okay. Now, the fundamental question comes in mind is, if earthquake forces are applied at the seabed at the greater water depth, how that is going to affect the response characteristics of a compliant structure whose superstructure is about 1 kilometer, maybe 1000 meter above the seabed. That is a very relevant question. So, now the question asked is, how earthquake forces will affect the superstructure of the platform. Okay, that is the question asked. Because we all agree that earthquake loads on TLP are not direct. What do you mean by direct? Had this platform instead of a TLP would have been a jacket structure. Would have been a jacket structure. Then in that case, earthquake forces applied here would have a direct effect on these members. So, if the structure is directly supported on the seabed, maybe using piles or maybe a gravity based structure using caissons, etc., then one can say earthquake loads will have direct effect on the platform. But in the case of TLP, when members are above water and it is only held down in position by a tendon, how the superstructure will have the consequence felt by the load applied on the ground at the seabed? That is a very interesting question. To answer this, let us try to write the governing equation of motion for the analysis. Of a TLP. So, mx double dot plus Cx dot plus Kx is f of t. We all know that TLPs are about 6 degrees of freedom. Therefore, these matrices are of order as written now. So, ultimately we will get a 6 by 6 matrix of mass, damping, stiffness and a force vector of 6 by 1. Looking into the basic characteristics of form dominated design of TLPs, one can infer the following. About the stiffness matrix, one can see that it is going to be a square matrix which is non-symmetric. It means k I j is not equal to k I j. You can refer more information about this on NPTEL lectures on dynamics of offshore structures. Further, it is a form dominated design which in sense any displacement given in heave degree of freedom will affect lateral displacements in surge or sway degrees of freedom. So, if I have a TLP which is position restrained by tendons, if I try to apply the lateral force on a TLP, you see that the lateral displacement cost is what we call as offset, which will be usually in surge or sway degree of freedom depending upon the wave direction. Simultaneously in parallel, this will also cause the displacement in the vertical axis, which we call as set down, which happens in heave degree. It means at least heave degree of freedom is strongly coupled with surge and sway degree of freedom. Now, one may ask me a question, how this statement is now important as far as analysis is concerned. We already said that any displacement cost in surge or sway is not a botheration as far as TLP is concerned, because TLPs are compliant in horizontal plane. What do you mean by compliant? Compliancy indicates that they are highly flexible in this plane. So, no botheration, but the botheration now comes because any displacement in horizontal plane is coupled to cause displacement in vertical plane, because I get heave motion now. Okay. This heave motion is a botheration, because the heave motion will affect the functionality of the platform. It changes the tension in the tether. If the tension in the tether exceeds the permissible axial stiffness of the member, it may even pull out, which results in flotation characteristics of the platform which can remain non-functional. So, interestingly friends, please note that any lateral force which is caused by an earthquake on the seabed will affect now the platform indirectly. Also, the coefficients of stiffness matrix depend on the buoyancy or what we call variable submergence effects. They affect T0 value significantly. But as per design, the change in T0 under normal loading, I am not talking about special loads, does not increase 12 to 15% of initial value. That is a design check, but under special loads like earthquakes, they may be even more, we may have to examine that. So, that is the botheration here. So, what we can infer is k I j are not constants, they are response dependent. Okay? They are response dependent. If we talk about the mass matrix, we agree that the structural mass is lumped in each degree of freedom . But mass matrix is also not symmetric because variable submergence effect. What is this variable submergence effects? When I have a system, when the system is under lateral load, when the system undergoes displacement, the immersed volume of the member is now changing. Okay? When the immersed volume of the member now changes, this invokes change in buoyancy. We call this as variable submergence. That is number 1. There is always a possibility two members are spaced in such a manner that one member will encounter a crust, other member will encounter a trough of the same wave. So, there is a possibility that these forces may get cancelled. So, we call this as stretching modifications, which is again another non-linearity. So, these issues will always make mass matrix unsymmetric predominantly for an unidirectional wave, predominantly, which is hypothetical. Only surge, heave and pitch degrees of freedom will be active, but in reality wave are multidirectional. Therefore, all 6 degrees of freedom will remain active, but yaw can be spared, yaw motion can be spared if the platform symmetry under load distribution and by geometry. So, yaw motion can be exempted or other 5 degrees of freedom will be anyway there. The next issue in the equation of motion is the damping matrix, which is also 6 by 6. There are many methods by which one can estimate damping. One can use a classical damping, which is 2 zeta omega m, whereas we will take up an example of using a Rayleigh damping, where C matrix will be some component of m and some component of k as well. Now, we are looking for seismic analysis of a TLP. We all agree that tension leg platforms are placed in wave environment. They do undergo large displacements. To make them compliant, they are designed for that. And they are estimated to be safe under such action, but in the presence of distinctly high sea waves, which is a special load, platform behavior is interesting. Now, one may ask me a question, why are we considering distinctly high sea waves in the presence of earthquakes? It is very interesting. By natural phenomena, when earthquakes are caused by sea bed movement, they generally result in wave generation of large amplitudes. Okay. So, sea quakes will be generated as an inherent characteristic when seabed movement happens. So, we are now interestingly looking at a platform in the presence of earthquake and distinctly high sea waves. Now, what is a distinctly high sea wave? The sea surface elevation, what we will now discuss as an input data for the platform, is critical. What do you mean by critical? The shape should remain steep, it should be asymmetric with respect to both vertical and horizontal axis. So, such sea waves are called as distinctly high sea waves as expressed by Kribal and Alsina. It is also a fact that shape of experimentally observed extreme waves are different significantly from the theoretical ones. This was stated by Zhao and Kim in 2000. So, this leaves a very clear conclusion to us that you cannot generate a distinctly high C wave experimentally, you should generate theoretically using the factor or the considerations given by Kreibel and Alsina. So, therefore, no systematic model is available to classify such irregular, steep and asymmetric waves. So, therefore, I can call this as special loads, which I call distinctly high C waves. So, we are now handling a problem with two special loads acting simultaneously in the given system. One is earthquake forces generated by Kanai-Tazimi power spectrum, or a parallel spectrum which is going to create the earthquake forces desired on the platform. The second is presence of distinctly high C waves which will be irregular, steep and asymmetric. Now, the question comes, how do we generate these waves? Because experimentally if they are generated, they are not going to suffice the requirement as similar to that of an theoretical waves. So, we should have a method, a mechanism, a program or an algorithm to generate these kind of waves theoretically. So, this can be easily generated using the classical non-linear kinematic wave theory. So, people have shown that using the classical Airy's wave theory, from a randomly generated sea surface elevation, using modified Pearson-Moskowitz spectrum, such irregular, steep and asymmetric waves can be generated with simple one parameter equation. Thanks to Pilato et al. 2002, 2003 and Michel 1999, who gave us the algorithm to generate such distinctly high C waves. So, the spectrum will have the governing equation with one parameter which is given by 8.1 10 power minus 3 g square by omega phi exponential minus 1.25 omega m by omega to the power 4, call equation number 3. Omega m in the above equation is called modal frequency. Usually it is taken as 0.46 hertz and S eta eta is the power spectral density function of the wave height with one parameter, that is the wave frequency omega. So, now in the present study, wave elevation, because we are bothered about the steepness, spectrum will not give you the steepness. We have to now say that the generated wave elevation should remain steep, should remain asymmetric, both about vertical and horizontal axis, to call this wave as a distinctly high C wave. So, let us now try to generate a wave of this order, whose wave elevation will be realized as discrete sum of many sinusoidal functions. They will have different angular frequencies, they will have different and random phase angles, so a typical wave elevation looks like this. Eta of t is summation of, because we are looking for discrete sum of many sinusoidal function, I equals 1 to n 2 s eta eta omega I, where s eta eta is given by the previous equation. Delta omega I, we are looking for a small component in omega, cos k I x minus omega I t minus phi I, equation number 4. In the above equation, k I is the wave number, omega I is the discrete sampling frequency, delta omega I is actually omega I minus omega I minus 1, the gap between the successive frequencies. N is the data point over which we are going to make the discrete sum, and phi I is the random phase angle. So, friends, using equation 4, one can now generate the sea surface elevation, which actually is dependent on the spectrum of one parameter, which is a modified Pearson-Moscow spectrum as recommended by Pilato et al. Researchers. So, look at the screen, a typical sea surface elevation generated using this equation is now shown. So, that is the Pearson-Moscow spectrum with one parameter. Based on this, using equation 4, a typical sample time history is generated. You can see the time history, and highlighted wave profile has a concave front. You can see that the concave front, it is a continuous function in time domain and it has got a convex rear. So, the wave profile remains asymmetric about the vertical axis, asymmetric about the horizontal axis, and that can be called now as distinctly high sea waves. Having generated the sea surface elevation, now after generating sea surface elevation, which is irregular, asymmetric and random, and of course causing distinctly high sea waves. We have now generated a sea surface elevation which is not uniform, but an irregular wave which is having a concave front and convex rear, asymmetric about horizontal and vertical. Further, this distinctly high sea waves is applied as a special load on a TLP along with seismic forces, which causes displacement on the seabed. So, friends, it is now interesting that the problem is well defined. We have earthquake forces plus distinctly high sea waves, which makes it as a special load. The example system is a compliant structure like a TLP. It is expected that this structure should not have any effect because of earthquakes, because it is compliant, but the example will clearly show you there are serious consequences on this structure because of this combination of special loads, which we will see in the next lecture as a continuation. Thank you very much.